Now my next example sounds really hard, and I've chosen this one because it does sound hard. But once you see the solution, you think, oh yeah, I can do that. So the question is, how do you prove that the diagonals of a cube intersect each other? As a cube. Okay. How do you prove that the diagonals? Now when I say diagonals, we do mean the longest diagonal. So I'm talking about from here to here, okay, and from here to here, okay, or from here to here. How do you prove that they intersect each other? It's quite hard, isn't it? Okay. Well, we start off with a diagram, of course, all right, and what I'm going to do is I'm going to just add to this diagram all of the edges of the cube, okay, and then I'm going to label it, so you've got points O, A. Now I've labelled that O, notice, so that could be the origin on a set of coordinate axes. How am I going to do this? B, C, right? And then up here, I'm going to go for D, E, F, G. It's not a two-dimensional shape, so you don't call it A, B, C, D, E, whatever. Okay, so there we are, there's a cube. Okay. Now, what do 3D coordinates look like? Okay. Now, 3D coordinates are very simple. So with 2D, you've normally got X, Y, but with 3D, call that the X axis, call that the Z axis, and call that the Y axis. Okay. Notice how that, okay, shows that the axes are parallel to each of these three edges of the cube. Alright, that's quite important. So if we were to label these in terms of that's the I direction, that's the J direction, that's the K direction, okay, you'd have some multiple of I here, some multiple of J, some multiple of K. Now, as it happens, I'm just going to rather simply call them A, B, and C. Okay. The length of them doesn't really matter at this stage. Okay, that's what I'm going to do. Alright, so I've just started it off, and I've not actually done anything in terms of answering the question. You know, if this was an exam question, which it's not, this is 0 marks so far because I've not actually done anything. What I'm doing is I'm just trying to make the geometry problem into a vectors problem. Now it looks more like a vectors problem, doesn't it? Okay, so what do we want to do? I want to show that two diagonals intersect each other. And the two diagonals I'm choosing are the diagonals OE. No, that's stupid. That's not a diagonal, that's just from there to there on the face. Okay, so OF, so from here to here, that's the longest diagonal, isn't it? And I'm going to show that it intersects with, let's do AG. Okay. So, of course, because it's vectors, we're going to have to consider what the vector OF and what the vector AG are going to be. Yeah? So we'll go ahead and do that. So, OF, because it's easier. Okay? What is vector OF going to be? So, from here to here, it's just that, isn't it? Okay? So it's A plus B plus C. Remember, that's A, that's A, that's A, that's A. And all the ones parallel to that, because it's a cube, they're equal length, they're all C, and those are all B. Okay, so it's just going to be A plus B plus C. Okay. Now, let's just, so I was going to say something else, but let's just move on. Let's do AG next. Okay, so AG, what's that going to be? So from here to here, so we've got to go that way, then that way, then that way. Yeah? So that way, that way, that way. So how best to write this? So negative A plus C plus B. That's, I'll tell you let's write it like that, shall we? Negative A plus B plus C. Just, it's easier. Okay. Now I'm just going to draw in blue what one of the diagonals looks like. Okay. It's kind of tricky drawing these things in with three-dimensional shapes. Okay. So that's the one diagonal. Okay. Now A to G. Okay, it's going to look something like this. Okay, I want to show that they intersect each other there. All right. Now, how on earth do we do that? Okay. Well, what we've got to do is you've basically got to write down just a letter for that intersection point M, and write down a vector expression for what point M is. Okay, so what I'm going to do is I'm going to start off with what OM is. Okay, so from O to M, the origin to M, and big hint for you. Okay, try and use the origin wherever possible. It's much easier. It's literally 0, 0, 0, and it makes things much easier. Okay, so no matter where your shape is, just move it to the origin, and then you find it easier. Okay, so OM. What's an expression for OM? Just kind of giving you some thinking time. Okay, so we're going to write lambda A plus B plus C. Now you might have been thinking, let's write half A plus B plus C, because M, I've kind of used that because it's a midpoint now, okay? But you know that where it intersects, it's going to be halfway along that line, isn't it? Okay, we know that, but we can't assume that because we're doing a proof here. Okay, if we assume that, the whole thing just falls apart. You can't prove it. Okay, so what we're going to do is we're going to state that OM is somewhere along that line. It's lambda A plus B plus C. Okay, does that make sense? Good. Now, also, M lies along the line A to G, doesn't it? Okay, so let's work out an expression for vector AM. Okay, so from A to M. Okay, so that is going to be similar, isn't it? Okay, but we use a different letter there. We're going to use mu, and it's going to be some multiple of AG, isn't it? So mu times negative A plus B plus C. Okay? All right. Now, let's get another expression for OM. And this is a lot of what most vectors problems boil down to. Trying to get two separate expressions for the same vector and then set them equal to each other. So we've got OM equals this. I want to get a new expression for OM using that. Okay, that's one thing I've came to like about vectors, is that to get a expression for OM, you can choose whichever path you want. So the paths I'm thinking of are straight away from here to here, or you can go from here to here to here. And that's what we're going to do. Okay, we're going to go from O to, I'm going to write that down. We're going to go from O to A, and then plus A to M. That pathway, OA plus AM, will actually do it for us, won't it? Okay, so that is O to A, which is A, plus mu negative A plus B plus C. Okay, now what I'm going to do is, I'm going to tidy it up a little bit. Remember, this is a bit like having I, J and K components. All right, in mechanics problems, vectors are so much associated with mechanics, okay, and once you're happy with the I, J, K thing, things like this make much more sense, okay. So I'm going to write it as A, and then 1 minus mu, and then plus B. So I've not written that down nicely, okay, because I prefer to write the scalars first. So I'd normally write 1 minus mu A, but I'm going to leave that. But I'm going to write it as mu B plus mu C. All I've done is expand the brackets a little bit, that's all. Okay. Now, those two are exactly the same, because we've got OM equals this, OM equals that. Right? So we're going to put these equal to each other. Okay. So we're going to say that that is the same as that. Okay. But what that means is, okay, we can equate the A components, the B components, and the C components. Now, I could have called those I, J, K, couldn't I? Yeah. So I could have been calling that negative I plus J plus K, I, J, K. And that's one thing that should help with vectors quite a lot. Notice that, with the parallel vectors, you treat them like a set of I, J, K components. I'm hoping this makes sense. Okay. This is the trouble when someone's not there. I can't judge people's reactions. Okay, because like in a standard math lesson, I'm talking about vectors. People generally aren't nodding and going like, yeah, I'm getting this. People are like, please tell us this is the hardest question you're ever going to set us. Yeah, so I'm hoping that it's kind of making sense. All right. So I'm going to create the A components, all right? So that means I'm going to have lambda A is equal to 1 minus mu A. So lambda equals 1 minus mu, okay? And if I equate the B components, I'm going to have lambda equals mu. I don't need to do the other one, but if I did, I'd have the C components, lambda is equal to mu again. All right? The fact of the matter is I only need two equations with two unknowns. Those are the simultaneous equations. Okay, they're quite easy to solve. Just add them together. So you do that plus that. So it gives you 2 lambda is equal to 1. Gives you lambda equals 1/2. Can you see that? It's very magical, that is. Okay, that lambda equals 1/2. Okay, that's basically proving to you why this point M is the midpoint, because now we've just shown that OM is 1/2 of A plus B plus C. So that's the proof that M is that midpoint there. Okay. What we should then do, and I've kind of run out of space to do it, is to substitute in. So I'm going to write in a different colour up here, if you don't mind. Okay. So you've got OM is equal to 1/2 A plus B plus C. So that's from that one. Okay. And then from this one, we're going to have OM is equal to, we're going to work out mu's as well. So because lambda is mu, let's just put in that's also equal to mu. So A, and then 1 minus 1/2 plus 1/2 B plus 1/2 C, like that. And then when we simplify that, 1 minus 1/2 is just 1/2. So you get 1/2 A plus 1/2 B plus 1/2 C, which you can write as 1/2 A plus B plus C. Okay, showing you that they must intersect, because we've ended up with exactly the same. What would happen if they didn't intersect? Okay. Well, you wouldn't be able to solve those equations. And again, that's something else that vectors is about. Proving whether something does happen or doesn't happen hinges on whether you can solve the equations you end up with. So if you can solve the simultaneous equations, okay, and when I say solve them such that lambda and mu work in both of them, then you've done it. Whereas if you end up with equations that are impossible to solve, then it can't be done. Okay. Anyway, there you go. How do you feel about that example? You're like, yeah. But, yeah. To be honest, vectors is kind of a bit like that. But again, notice that the slow build-up of it, the diagram, writing the vectors. Okay, it's there to try and make things easier.